Hi everybody, I'm Catherine. Thank you, Ruben, for the introduction. So today I want to start my presentation by talking to you about plastics. Now I'm sure as soon as I say the word plastic, most of you in the audience will automatically think plastics are bad. And that's not really surprising considering all the media coverage of plastics most recently. If any of you watch Blue Planet 2, you'll have seen a little turtle with a plastic straw up its nose, and that's because of all of the excessive plastic waste that's left in our oceans. Scientists have now been able to quantify this amount by saying that for each foot of coastline there's at least 5 bags of plastic. Plastics also become more expensive to recycle, so as you can see there's a lot of reasons why people would automatically think plastics are terrible. But hopefully I'm going to turn this idea on its head slightly today. And I'm going to start by looking into what actually is a plastic. According to the Oxford English Dictionary, a plastic is defined as a synthetic material made from a wide range of organic polymers, such as polyethylene, PVC, nylon, etc., that can be moulded into shape while soft and then set into a rigid or slightly elastic form. And the area that I want to concentrate in this definition is this organic polymer. So what's a polymer? A polymer is defined as a substance which has a molecular structure built up chiefly or completely from a large number of similar units bonded together. So as polymer chemists, we would call these similar units either monomers or repeating units. So essentially, a polymer is just the same repeating unit repeated over and over and joined together to form your polymeric chain or polymeric backbone. So there are actually a number of natural polymers that exist in the world around us that you may not even be aware of and may not really come to think of. So for example, one kind of category of natural polymers are polysaccharides. And a saccharide is where the repeating unit here is the sugar. So for example, starch is a polysaccharide. So a potato is actually a natural polymer. Another example of a polysaccharide is cotton. So as you know, we find quite a lot of cotton within our clothing, so we actually wear polymers. Another category of natural polymers are polyamides. An example of one of these are enzymes. Now enzymes work within our body and within the natural environment to catalyse reactions all the time. Another example of a polyamide is protein. As you all know, we eat proteins. Proteins also exist in our bodies. And the final category of natural polymers that I'd like to draw your attention to are polynucleotides. Polynucleotides. So this means that a DNA is actually a polymer. So we're made up quite a lot of these natural polymers. So hopefully I'm trying to draw you around to the fact that some polymers are actually good and they actually make up a lot of the environment around us. Now as polymer chemists, we try and take these very sophisticated systems and mimic them in nature so that we can use these sophisticated systems, for example, in the biomedical field. So these are just to give you a flavour of some of the polymers that exist in the biomedical field. There's thousands of them. These are just a few that I came across. So for example, we have the prosthetic foot. There's a biodegradable and reusable EpiPen. There's biofix, which are inserted during surgery to encourage the regrowth of bone. There's Proflex mesh. Again, these are used during surgery to kind of like swab up blood. And finally, Glidol wafers that Ruben introduced earlier. And as you know, these are used as local drug delivery systems for the treatment of glioblastoma. So this leads on to the idea that polymers not only they exist naturally, but we can also use them as drug delivery systems. So how can we do that? So as I said, we have our polymeric chain, and we can manipulate this chain so that we have at least 2 sections to it. Hydrophobic, which is shown in red, and hydrophilic, which is shown in blue. Now hydrophobic basically means water hating, and hydrophilic means water loving. So when we introduce these polymeric chains into a hydrophobic system, the hydrophobic area will clump together to form a core, and this will be surrounded by a blue hydrophilic outer layer. So essentially you have this nanoparticle made up of 2 sections, the core and then the outer layer. So if you introduce a hydrophobic drug into the system, as the polymeric chains come together to form this nanoparticle, it will encapsulate the hydrophobic drug in the centre, and then it will be covered by this hydrophilic outer layer. So I've spoken about nanoparticle, and Ruben mentioned earlier micro, but it's kind of hard to visualise of how small we're actually talking. So nano, as most of you know, will be 10 to the minus 9 metres. But this means that a nanoparticle is typically the size of 1/100th of a human hair. So this is tiny, but it's still quite hard for us to actually visualise what this actually means. So I found this quite nice analogy to say that the size of a typical nanoparticle is to the size of a football, if the nanoparticle is the size of a football would be the size of the Earth. And carrying on with this football analogy, if a football is the size of a nanoparticle, how big are the brain cells that we'd be dealing with? So if a nanoparticle is the size of a football, a brain cell would be not just 1, but 2 Wembley football pitches joined together. So that's the kind of size we're talking about, and I'm hoping that's made it slightly easier to visualise. So why are scientists excited about nanoparticles? Well, as we've established, they're pretty tiny, so we think that we'll be able to use these to penetrate further into either healthy tissue or tumour tissue. So the reason we'd want to penetrate into tumour tissue is to get to the centre of the tumour core, so that for then the nanocarrier to be able to release the drug and have an effect. Why we might want it to penetrate further into healthy tissue, as you know with treatments such as glioblastoma, the tumour is removed, but then you have these residual tumour cells left behind. So if the nanocarrier is able to travel through the healthy tissue, it will then be able to reach the residual tumour cells and have an effect. The polymeric carrier also acts as like a protective case around the drug, and this has two benefits. The first one is that every drug has an active half-life, so it means it's only active for a certain amount of time, and this certain amount of time can actually be quite small. So if you apply a drug directly into a natural environment, it's going to start degrading quite quickly, which means it's going to have a very short amount of time in which it can act upon. So therefore it's not really going to be able to travel very far in its active form. So if you have this protective casing around it, it kind of protects this time bomb of the life expectancy of the drug. The second benefit is that it also protects the healthy tissue. So as you all know, chemotherapeutics or chemotherapy drugs are very toxic, but they're not necessarily selective just for tumour cells. They're also toxic to healthy cells, and that's why we see these side effects. So by putting a drug in this kind of polymer casing, we're actually kind of protecting we're also protecting the healthy cells from the drug's actions. So we believe that they'll have less toxic side effects, and therefore, because there's less toxic side effects, we'll actually be able to load more drug to have more of a potent effect when it's applied. We're also hoping that we'll be able to control the release of the drug, and I'll come on to that on the next slide. But the main reason why nanoparticle therapy is exciting is because it's not some far-fetched theory that's decades away from actually working and being in our clinics. There's actually formulations on the market as we speak, used in clinics worldwide. So as I said, we'd hopefully be able to control the release of the drug. And we can do this by comparing healthy cells and cancerous cells. Now, healthy cells and cancer cells have very different genetic makeups, but they also have different tumour environments, depicted here by these lightning bolts. So as polymer chemists, we can kind of take this information that we know about the tumour environment and try and build this into our polymeric chain right at the beginning, so that when we form the nanoparticle, we can try and control the release of the drug. So if we have our polymer chain, we can do some quite complex chemistry to add on these responsive linkers. And the idea here is that the responsive linkers, once triggered, would break apart and release the drug. After some more complex chemistry, we can add on our drugs to these systems. So what we'd hope is that when the polymeric chains with these drugs attached reach a healthy environment, nothing would happen because there's no triggers involved. But as soon as we introduce a trigger, this drug would be released because the responsive linker has broken down. So this leads, hopefully comes full circle to Rumen's talk with the PLGA-PEG paste. And the kind of overall aim of my PhD is, rather than just in kind of putting in chemotherapeutic drugs directly into the PLGA-PEG paste, we'd actually put in these nanocarriers that are carrying the drugs for us. So if we can incorporate these nanocarriers formulated into the paste during surgery, we'd then be able to release the chemotherapeutic drug-loaded nanocarrier. It would travel through the healthy cells and not have an effect on them, and once it reached the tumour cells, because of the tumour environment, the drugs would be released and it would kill the cell. So in conclusion, I hope that I've been able to show you that not all plastics are bad, but I do feel like I have to make a disclaimer. Most plastics are bad, so please don't go throwing them in the ocean and not recycle or anything. Hopefully you've understood that polymers can be used as drug delivery systems, and you may be kind of wondering where I'm at with this project. So I've done quite a lot of the chemistry, but there's always more chemistry to be done, so that's kind of a work in progress. But I've got my first batch of formulations that I'm currently doing cell work on. And as Ruben said, we've got quite exciting collaborations with Johns Hopkins and also another one with the University of Leuven in Brussels. So for future work, we'll hopefully be able to go over there and do some in vivo studies. But that's all. Thank you very much.